Video number 2 here about integration by parts. So I've shown you one example using the formula, and now what I'm going to do is show you tabular method, which tends to be a lot quicker, but you need to be able to use it correctly in some spots. If I guess I should say, there's some times where the formula might be more useful, but if you're savvy with tabular method, then you can kind of get away without using the formula at all. So here's how tabular method works. And what I'm going to do is do tabular method with this, and then I'm going to do tabular method to show you that it matches this formula right here. So what we do, and just come along for the ride, and I'll show you why it works. I do a dir side for derivative, and I do an int side for integrate. I take the one that is going to derive away. For example, this x right here, if I were to take its derivative once, I would get 1. If I take the derivative again, I get 0. So any polynomial, for example, x to the 6th, if I derive x to the 6th, I think 7 times, it'll derive away. Cosine will not do that. So I put on my dir side my x. And then I put on my int side my what is left over, which is, in this case, cosine x. And I take the derivative of this until it goes to 0. 1 is the derivative of x, and then 0 is the derivative of 1. From there, I integrate, and the integral of cosine is a positive sine x, and the integral of sine x is a negative cosine x. So now what I do is I go diagonally and I alternate signs. This alternating of signs is really this negative right here in the formula. So what do I get? Oh, and then what I do is I multiply along those diagonals. So let me zoom out just enough so that we can see the answer from our previous method. And watch what happens when I multiply. I get this times that is x sine x. There it is, x sine x. And then here I get a double negative. I get 1 times cosine x. So I get plus cosine x plus a constant. Boom. See how fast that is compared to, wait, what's u, what's v, what's the formula, right? I just throw it in the tabular method, do my dir, my int, dir till it goes away, int as much as I need to, and then multiply diagonally. I'm going to actually, before I show you why it works with the formula, I'm going to show you another one. Say I had x squared, the integral of x squared times e to the x. Notice this is one with a dx, sorry. This is one like the ones that I was talking about up here, or this one right here, where the u sub just doesn't line up. It's not set up for me to do the integral of, because this x squared doesn't match the u sub. If that was an x cubed, I could do u sub, but in this case I can't. So what I do is I set up a dir side and I set up an int side. Think about what I said a moment ago about how to choose what is the dir, right? Well, x squared, if I derive that enough, it's going to go down to 0. So let's dir it, x squared, 2x, 2, and 0. Now, on my int side, I got e to the x right here. Let's write e to the x. What's e to the x integrate to? Oh, e to the x. What's it? E to the x. E to the x. That's what's nice about e to the x, is it integrates and derives to itself. And now I go alternate plus minus. You may say, well, what about this? Well, that one would give me a, I'm not going to go there. I'm just going to go like this. All right, so what's this derivative, or what's this integral? Well, I will take the product along those diagonals. So I get x squared e to the x, then I get minus 2x e to the x, and then I get plus 2 e to the x, plus a constant. Boom. That's how fast that is. If I was to try to use the formula with this one, I would actually have to iteratively which means like do it a couple times, use the formula. So now let me try to make a connection between the formula and this tabular method. And I'm going to grab this and bring it, well, bring it down here. All right, so the formula is the integral of u dv is u times v minus the integral of, v du. If you're trying to remember the formula, the kind of acronym for it is ultraviolet voodoo. Ultraviolet voodoo. You see it? Ultraviolet voodoo. So ultraviolet voodoo. I don't know. I just prefer the tabular method. All right, so let's do a dir and an int. What I'm going to do is convince you that if I use dir int on this, that I will get that out. Okay? So watch. So what do I have? I'm going to let the u be the dir. Okay? What's the derivative of that? Du. I'm going to let the int, so that means like that's this piece right here. Okay? That's my dir side. Just like over here, my x was right there, and I wrote the x right there. So this is my u. All right, so next, I have a dv right here. That is all of this, okay? Which gives me, over here, dv. Well, what's the integral of dv? It is v. And now, watch what happens here. Normally, what I would do is I would integrate again, okay? But what I want you to see is that I can go plus, and then I can go back and do an integral. And actually, we can do it this way. Next, I will do the integral of that, right? So the integral of v, right? Because this is the int side. So if I do my dir int stuff here, I have u, that gives me du, the derivative, and I start with v, integrate it, it gives me v, integrate that again, I get the integral of v. And then watch what happens here. If I do my minus, my alternating signs, I get this guy is this guy. There we go. Now it looks better. All right, so if I do my alternating signs and products, I get u times v, that is this times that, the same way I did over here, x times sine x, bam. And then minus, that's this minus, and the integral of v with a du on it. And notice this is what I have right there. And you may be like, well, it's already written here. Why would you do all that work to show me that it's written again? What I'm trying to do is convince you that this formula is equivalent to this process right here. So hopefully you see that. One way to think about it, no, I'm not gonna go there. I'll save the next part for later. When we talk about back integrals and escape methods, which we'll do next time I see you. So you know what let's do? Let's do another example. I think you can handle that. Okay, we are gonna do the integral of x cubed sine of 3x dx. Now, this one, we're definitely going to use tabular method. And I hope you're at least, I guess I should say that I hope you're convinced that this is that tabular method matches this formula, and that if I go up to the top, that the formula has to be true because of product rule. So hopefully you're convinced that we are allowed to do this. Let's go. What do you think is going to be on the dir side? X cubed. Good job. What do you think is going to be on the int side? Sine of 3x. Good job. Now, I got a dir the x cubed, 3x squared, 6x, 6, and 0. That's a lot of rows. All right, so next I integrate. Sine integrates to cosine of 3x with a negative and a 1/3. The 1/3 balances the chain rule that would come from that 3. If I derive this line, I get that line out. Then I get a negative 1 over 9, not cosine, my bad, sine of 3x. And then I get a positive 1 over 27 would be 3 times 9, cosine of 3x. And at this point, I'm going to check to see if I have enough lines on the inside. Nope, it looks like I need to do one more line because I need to get down to the spot where I hit that 0. So I get 1 over 81 sine of 3x. You may be wondering why this one's positive. Well, cosine, I've got a negative sign here, and that's actually what cosine derives to, right? Cosine derives to negative sign. All right, so we go wha-bam. And now I can just multiply along my rows. What does this integrate to? It gives me negative x cubed over 3 cosine of 3x. That is the first product. All right, then 3x with, oh, sorry, I got to do my alternating signs, plus, minus, plus, minus. All right, so look at that. I get a double negative on this one, and, I'll write it out. So I get plus 3x squared over 9 times sine of 3x. And then my next one is positive again. So plus 6x over 27 cosine of 3x. And then my last term is negative, and I get a minus 6 over 81 sine of 3x. Now, I am going to pause for a moment. I rewrote the line. I should include my plus c and my plus c. Some of these things simplify here. If you look here, I've got a 3 over 9. That's actually a 1/3, so I'll write over 3 there. 6 into 27. Well, I know that 3 divides into 27 and gives me 9 in the denominator and then a 2 in the top. And then again, 6 divides into 81 and gives me a 27. Remember, I got this 81 by multiplying the 27 by 3, and then leaves me with a 2 on the top. So my simplified version at the end is that. So again, let me just review real quickly. We started with a formula. I didn't tell you where it came from. Then I showed you that that formula comes from product rule, just manipulating it a little bit. Bam, we get this thing, okay? You practiced a little bit. I talked about when we need this formula, right? There we don't have the u sub. Then we did this problem using the formula. It was kind of messy and confusing and took some time. And then I said, oh, we can just do this tabular method thing. Bam, bam. And then I showed another example of tabular method that gives me this. It's a little bit longer, sort of multiple iterations of the formula being used. And then I tried to convince you that this formula up top, this formula is equivalent to using tabular method by just doing the dir of one side and the int of the other, and then bam, I get the formula out. So the formula is good to go. Makes sense. It matches what we got from product rule above. And then we did one more. The one thing that may not make sense is why I can do this over and over again, why the tabular method can keep going. It should make sense why we get at least these 2 rows of tabular method. We'll try to get to that later. And then the other question is, what happens if we don't get a 0 here? What if something just keeps going, right? What do I do? How do I deal with that? And that is something that we will talk about soon, and I like to call that the escape method. So, see you soon. Later.